Today, we're going to enter the wild, wacky, wonderful world of GPU computing. We're going to be looking at two different ways of doing the GPU computing. One is called Cuda, one is called OpenCL. Cuda was developed by NVIDIA. It stands for Compute Unified Device Architecture, but basically it means you can write in something that looks like C and it will run on a GPU. So let's go see how this is going to work. Here's how this is going to happen. Really, your program is in two pieces. There's a piece that's going to run on the CPU, and there has to be a piece that runs on the CPU because that's what you're logged into. That's what you're sitting in front of. You can't reach down, put your hand in the chassis, reach down into the graphics card and say, boom, run this program. No, no, no. You have to run it on what you've got. That's the CPU. However, we are also going to write a chunk of code that is going to run on the GPU. And so think of it this way. You've written a C program. It will look like a C-ish program. Some of it is host code to run on the CPU, and it's going to set things up, if nothing else. You're going to compile it with a C compiler. But part of that code is going to be designated, it's going to be marked as this is GPU code. It is CUDA code, and it will be compiled with the CUDA compiler and linker. Now, CUDA is going to manage all this for you, which is really nice. You go ahead and run your program, and when you say, and now I want to execute this very, very special function, it's going to run over to the GPU, actually run it over there with many, many, many threads, and then bring data back. And you can do this, again and again as much as you would like. We're going to do it once, get some computing done, bring the results back, and we're done. Okay, so let's go see a little bit more about GPU computing. If I was going to multiply two arrays together, and that's going to be the demonstration of this. If I was writing in normal C, C++, I would do it like this. I'd have a function called array_mult, and I would put in a for loop, and I would do this. C of I equals A of I times B of I. Okay, in CUDA, we would do this. Now, first of all, you look at this code and you say, oh gosh, what is this gobbledygook here? And where the heck did my for loop go? And that's usually the thing that's most disconcerting about working from CPU code, say OpenMP, into GPU code such as CUDA or OpenCL. OpenCL would look the same way. Where is the for loop? Well, there isn't a for loop, or I guess in essence, there is a for loop. It's an implied for loop. It's an implied for loop because what you're going to do is you're going to run this on many, many, many threads. Okay, well, which thread does this chunk of code have access to? Here. GID stands for Global Identifier, and I'll explain what all this stuff is. But just know that by the time GID gets set, it's a number between 0 and the length of the array -1. So if let's say that we've got 50,000 elements in the array is dimension 50,000. GID is going to be a number between 0 and 49,999. And this is really doing the work. Okay. And so many, many threads get created. That's how GPUs do what they do. And each one is responsible for doing this line of code on one of those 50,000 elements. Okay, so there really is a for loop here. It's just not obvious like it would be in C or C++ code. Now, how does this work? Well, the architecture of a GPU is the GPU's workload gets divided into blocks, and it's a grid of blocks. So each one of these yellow things with these wiggly threads, those are threads, each one of those is a block, and it's arranged in a grid. It doesn't have to be really, it's just a convenience. Like a lot of times we do 2D array problems in GPU world, and it's just handy that you can think of the blocks as being in a 2D grid. They're not. Each block has a grid of threads. And again, the threads can be thought of as being arranged in a 2D block. You know, they're not, but sometimes that's convenient to think of them that way. But anyway, just think of it this way, is there are blocks and blocks have threads. And each one of these threads is going to be executing this code. This code is known as the kernel. Each thread is going to be executing this kernel, but it's going to end up working on a different global identifier. Okay, so block is made up of a grid of threads. The threads have thread ID numbers. Your program, their Cuda program, will use these thread ID numbers to turn them into a GID that will pull the right data from memory and put it back where it belongs. These threads can share data, they can synchronize. Threads within a block can synchronize. And that's very special because within a block, you know, think of the yellow robot diagram. In the block, each thread is executing the same instructions, but on different data. Just like each gripper on the robot is doing the same motion, but on a different grapefruit, okay? The architecture of a GPU typically puts 32 of these threads in a group, and they call that a warp. Now, warp is a loom weaving term, you know, kind of get it. It's a group of threads, a warp. It's called a warp. And there's 32 threads in there. And you get to specify how many threads you want to execute. So 32 of them are going to be executing the same instruction. Just like on the robot diagram, 6 grippers are going to be executing the same instruction. In the same way that only using 4 of the grippers would be a real waste, using anything less than 32 threads would be a real waste. And actually what we really do is we use more than 32, okay? Because if the instructions that a warp is executing need to stop, like say the instruction needs to go out to memory and bring something back, what the GPU is capable of doing is pulling that group of 32 out and replacing it with another group of 32 so that it's got plenty to do while the first group of 32 is waiting. So we typically don't just use 32, we do 64 or 96 or 128 or something like that. And I'll show you an example of where we can play with that. But yeah, within a block, the threads can synchronize. They're all executing the same thing. They can synchronize with each other. With different blocks, they can't. That is, there's no communication between different blocks, but within a block, yeah. Okay. Yeah, I almost didn't put this in. It's a little kind of weird, but you know, again, think of it as a warp being a group of 32 threads. If that instruction that the entire warp is executing needs to block, waiting for something like a memory fetch, it's going to swap that 32 out, bring in another group of 32. And so really you can sort of think of it as, well, okay, here's warp number 8 and it's executing its instruction 11 and it swaps out for some reason. But oh, now look, warp 1 is ready to run. Let's bring it in and it executes one of its instructions. But oh, now it blocks. Well, let's bring in warp 3. But by now 8 is ready to run. Oh, and then 3 is ready to run. So really this swapping out is just trying to keep the GPU busy. You know, you've got this GPU. To have it go idle is really a waste of a good GPU. Now, fortunately, you don't have to worry about this a bit. You just have to know how to set everything up. Okay, threads actually can access various types of storage. Global memory is the big memory that's out on the graphics card. there is something called constant memory, which I'm pretty sure at this moment is stored in global memory, but maybe someday there will be special memory on the card just for holding constants. Then within each work group, that is that group of threads, there is shared memory that each work item, each thread can get access to together. We're not using it in this example, and I guess we won't in any of the CUDA examples. We will use it um, in our one of our OpenCL examples. And this is the same architecture, whether you're running CUDA or OpenCL. Can you imagine how awful that would be? Is you want to run a CUDA program, so you turn your machine off, you pull out the graphics card, you plug in the CUDA card. Then you want to run OpenCL, so you shut down your machine and you pull out the card and you plug in your OpenCL card. No, fortunately not. It's the same card, same GPU hardware. So OpenCL and CUDA really both have this model, so they can run on the same cards. So yeah, these are the different kinds of memory. And I think this same slide is in the OpenCL notes, but the registers are on the chip and the thread uses a bunch of registers. There's some private memory. This is for like local variables. One thread uses those. There's that shared memory that all threads in a block can get access to. There's global memory. It's off the chip. It's elsewhere on the board, and all threads and the CPU can get access to it. The CPU, and this is always called the host, and the GPU is always called the device. That's just sort of the standard terminology. And you'll see this in the sample code. Things that are like meant for the host begin with I begin them with an H. Things that are meant for the device, I begin with a D, just to try and keep straight what's going where. All right, each thread has its own registers. Yeah, each block can use some number of registers. You're not going to run out of registers with the examples that we're doing here. It is possible to run out of registers if your CUDA or OpenCL program is complicated enough. Yep, the number of threads per block that you specify, it better be a multiple of 32, otherwise you're underpowering one of the warps. Well, and again, I'll show you an example of trying different numbers of threads per block and what that does with the performance. All right, these are some built-in variables that you put in your program. I'm sorry, that you put in your CUDA program, and these get filled these get filled while the thread is running. So it's a built-in variable, but it'll be different. And this is how it figures out the global identifier. They're called dim3. That's really an int dimension 3. Okay, so this is what you saw in the sample CUDA code. So this is the, and you can have .x and .y. Because this is a 1D problem, we're just going to use the .x part. So this is how many threads in a block, and this is which block we're on. And so this multiplies out for whatever block we're on. This will tell us how many threads came before that. Then we ask, well, what thread am I within that block? And that gives us the global identifier. Okay, so we are, say, in block 4. That means 3 blocks came before us. We find out the size of each block, how many threads in each block. We are going to have 4 or 3 of those. And then in the 4th one, this is where we are. Add that to what came before. Here's where we are. That's the global identifier. Okay, and this global identifier will be different for each thread that runs. For a 2D problem, we would take the Y's into account. It's a little more complicated, but only a little bit. And again, we end up with a global identifier, and that's which one we go get out of global memory. There are Cuda functions that you use in your program. By the way, these are double underscores. So underscore, underscore device, underscore, underscore. This is how you flag where things in your file get executed. If I've got a function that I want to run on the GPU and have it be called from a GPU program, I flag it as device. Okay, and then the compiler knows how to set this up. If I have something I want to call from my C program, but have it run on the GPU, I flag that as global. And if I have something on the host that I want to run on the host on the CPU, I flag that as host, or I don't flag it at all. In that case, it's a C function, okay? So here's the trick. The trick is that when you are in your C program and you want to fire up something to happen over on the GPU, well, you call it as if it's a function, and it's got a parenthesis and arguments just like a function does, but it's got these triple less than and triple greater than. And NVIDIA calls those chevrons. So the triple chevrons, there's between the chevrons, there are two numbers, a number, comma, another number. They're both this dim3, but it's the number of blocks and the number of threads per block. And the product of those two is the number of things you're doing arithmetic on. So number of blocks, number of threads per block. You get to specify this. The chevrons flag that this needs to be executed over in the GPU. Okay, so that's this process. Send or run the GPU kernel. It's just like calling a C, C++ function like this, parenthesis, arguments, 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 except it's got that chevron stuff because it has to allocate so many blocks and so many threads per block. I'll show you this in the code. Okay, so this is one of my own experiments with number of threads per block. This was 8, 16, 32, and so on. We know that with a warp being 32, anything less than that is really underpowering it. So here's 8, and sure enough, the performance, is, well, of all the colored curves, this is the most abysmal. 16, only a little better. So 32 is kind of a baseline of that for any problem. That's the least you want to have. Now, if I do 64, then there's a spare set of 32. So when one set of 32 it goes idle, pull that out, bring in another set of 32, keep going. So you can see that 64 gives you a really handsome performance increase over the 32. And 128 gives you another jump, but you can see that 256 doesn't really help you that much. So in this case, I would probably just leave it at 128 and just allocate more blocks. But anyway, this is the kind of way you think about it. The number of blocks is the data set size divided by the threads per block. Oh yeah, and if we invert the graph, here's what we get. And again, you can see that these curves up here are topping out at about 128. And then increasing the number of threads per block doesn't really help, and in some places harms, which you often see in these kinds of curves because they're spending more time swapping in and out and less time computing. You can also see that, like OpenMP, let's go back to here. Small data set sizes are not a good use of a GPU, are not a good use of GPU parallelism. There is a certain amount of overhead with setting up Cuda or OpenCL threads and all of that. And so if you've got a small data set size, you're not going to end up with a great aggregate performance. You can see here where we've got enough threads allocated that as you increase the data set size, your performance, millions of multiplies per second, increases quite a bit. Okay, so this is how you think about assigning numbers of threads per block. All right, getting CUDA programs to run under Linux. This is what a makefile would look like. And I'm going to show you this in a moment. We're going to run something live, throwing caution to the wind. Okay, the compiler you're going to use is called NVCC, NVIDIA C compiler. It's the CUDA compiler. And your CUDA code is going to be embedded into your C code. They're going to be in the same file, and that file ends with .cu for CUDA, not .c, not .cpp, .cu. So remember that. Different file name extension, different compiler. CUDA is up to version 12 as of right now. We have so many different graphics cards on so many different systems around here. The commonality is CUDA 10. So if you put CUDA 10 in your makefile and your bash scripts, it'll work anywhere at Oregon State. Okay, you can use 11 if you want. You can use 12 if you want, especially if you're on your own system. But there will be, if you use 11 or 12, there will be some systems at Oregon State where it just won't run. Either the compiler will print out really insulting messages, or it will just run and hang. So there's no features in 11 or 12 that we're going to need for this class. Okay, so this is what a makefile would look like. Or if you just wanted to type it all in, this is what you would do. The math library, it's assumed, is already there. Under Visual Studio, this used to be a pain. Visual Studio, as of, I think, 2019, has made this a lot nicer. And if you don't have Visual Studio, you can go get it. You can go get it for free as an Oregon State student. Here's how you do it. Don't get one of the cut down versions. Get the enterprise version of whatever year you want to have. Okay, in Visual Studio, File, New, Project. Okay, and that's what you would normally do. But here's what's interesting. When it says create a new project, and you've got all these, but, and I don't know why they didn't put the word CUDA right here, but if you come here into the search for templates and type CUDA and wait a few seconds, it will come up with this whole set of things that it will do for you to set up CUDA. In Linux, NVCC is available. It's produced by NVIDIA, and actually it calls G++ to compile the non-GPU code. But over here, Visual Studio wants to control everything. And so by flagging this as, hey, this is a CUDA project, what will it do? It will bring in the NVCC compiler into Visual Studio. So this is great. Before they did this, this was a horrible pain. All right, so this is what you do. Same thing as normal in Visual Studio. Give the name you want for the folder and your project, hit create, and so on. And what Visual Studio will do is it will write a C program for you and will write a kernel for you. Okay, so yeah, we're doing multiply. It's doing add. And here's how it's setting it up. And it's setting it up really small. That's why it's getting away without having to worry about multiple blocks. Okay. And if we scroll down here, we would see the chevrons and all that. But basically, what you would do is you would replace the kernel code with your kernel code, and you'd replace the C code with your C code, and off you go. And if you want to use CUDA and OpenMP together, there's no reason you have to. You can. The NVCC compiler, you just have to tell it, hey, what's coming after this is a cross compilation. Don't treat this as anything to do with CUDA. It's treating it as G++ isms. So yes, you can do that if you want to. There's no reason you have to. All right, one last thing. If you're using multiple GPU cards with CUDA, you actually can go get them. Like every CUDA instruction will do something on the current card. And so all you really have to do is just set what the current card is. If you've got two NVIDIA cards in your home system, well, you can ask how many are there. And then when you say CUDA set device 0, it's going to use the first one. And when you say CUDA set device 1, it's going to use the second one. So all CUDA commands work on the current device. All right, this is the end of the CUDA notes, but it's not the end of our discussion. Here we are. We're over on a Linux system that you have access to. It's called Rabbit. And we have our array multiply code. So let's go look at that. vi array mul.cpp. And I know you're going to do this because this is what you're used to. You're going to say .c or you're going to say .cpp, and then it's going to go like this. Oh, there's nothing there. Well, that's because there's nothing there. It's a .cu. So array mul.cu, and there it is. Okay, so up at the front, yep, there are some helper functions. This is a standard CUDA runtime. Here we're setting threads per block like we've done before. We're setting it up so there is a default value, but if we want to, we can set it from the compiler. The NVCC compiler knows all about that minus capital G. Here's our data set size. In this example, we're just going to leave the default, which is 8 meg. Okay, so here's our 3 arrays, and because they begin with a little h, that means they're meant to live on the host. Okay, that's my convention. Data variables that are meant to live on the host, I typically begin with a small h. If they're meant to live on the device, I begin them with a small d. Okay, here's a CUDA check error. It'll tell you what line certain errors came on, but heck, you're not going to make any errors. Why would you ever need this? All right, here's our array multiply, our kernel function. Underbar, underbar, global underbar, underbar. That's a flag to the compiler, is get this ready for the GPU. We're passing in 3 arrays. Here we're doing our global identifier. And oftentimes we do this. What this is if your data set size comes out to be a nice even multiple of block size, you don't have to worry about it. But if your data set size is not an even multiple of block size, you'd better do something like this. Okay, so this is the kernel code. Here, we've not flagged this, which implies we want this to run on the host. Here, we're setting the H arrays. Okay, DA, DB, DC. ABC means it's the same as the HA, HB, HC, or at least the purpose is the same, but it's on the device. And if you were on the CPU, you would say malloc, allocate memory. Here it's CUDA malloc, and it's about the same kind of thing. We're passing in it's going to fill DA, DB, DC, and it's going to allocate this number of bytes. All right, so down here, CUDA mem copy copies over to memory. So up here, we've allocated memory over on the GPU, and we've given ourselves, well, they're not pointers. They're not the real memory address. They're probably indexes into a table, but it's what CUDA needs. And here we're going to copy, okay? And this is a flag, memory copy host to device. It's always second argument gets copied to the first. Okay, so second argument gets copied to the first. So we're copying the host arrays for A and B over. We don't need to copy the C array because that's what's we're filling. That's what's coming back. So here's our dim3, which is really an int 3-element array. The number of blocks is our data set size divided by however many threads per block that we want. And 1, 1 because it's a 1D problem. Threads here. Okay, this is how you set up the timing. And we'll let the GPU do the timing on this one. Okay, so all of this is how you set up the timing and click the stopwatch. Here is the call. We're calling a function called array_mul. We're passing in A, B, and C, which are really pointers to where that memory is in the GPU. And we're telling it, well, what we set up here is how many blocks and how many threads per block. That's what goes in between the chevrons. Array_mul is the name of the function to call. So this is one of the cool things about Cuda, having you put all your code in one file. Each half knows about the other. They were compiled together. You know, it's like siblings that were raised together. Whereas at OpenCL, we're going to put your C code and your .cl code in separate files, although that has an advantage all of its own as well. Okay, so we will call the kernel, and then we will wait for it to be done. Okay, and this will give us back the elapsed time in milliseconds. Okay, and we'll turn that into seconds. And then we will turn that into multiplies per second. And then to give us a more manageable number, we'll turn that into millions of multiplies per second. And then we will print them out. Okay, and we'll set this up for CSV already, but we're going to print out the data set size, threads per block, and so on. Here's how we bring it back. Now, since we're doing benchmarking, we're not even checking the results, or I put code in here to check the results. But now we're copying device back to host. Again, it's always the second argument gets copied into the first argument. So there we go. And then we can free everything up. We can clean everything up, which is good programming style. So there we are. And so if I type make, or I can, let's see, let's look at the make file. There we are. Just like in the notes, if you want to use CUDA 11, use this as the path it's been commented out. If you want to use CUDA 12, use this as the path it's been commented out. 10 will work everywhere. And here's where the NVCC compiler lives. And we're going to use that. And this looks just like compiling with, say, G++. So if I say make, or I can say, well, there's only one thing to make. So I'll just say make, and there we go. And it's compiled. And so now if I run this, it will default the number of threads per block. It will default the data set size. And there's what we get. We get remember, this is in millions of multiplies per second. So this is 14 giga multiplies per second. Wow. Yep, we are printing it out in megas. Okay, so that is, okay, so there you see some of the power of the GPU. It is in millions, so it's doing 15 billion multiplies every second. Not too shabby. All right, if we want to do it as a loop, like you are running one of the CUDA assignment, well, there we go. I've just done it in one for loop, but you can do two nested for loops like we've seen before in Bash. Here we're using NVCC, we're doing minus capital D to get it into the defines, and there we go. So let's run this. Oops. And I can just type it because I've done some things with the flags. You might have to type bash space loop.bash, but here we go. Okay, so if I'm only using 8 threads per block, again, I'm wasting 3/4 of the threads that the block has, and sure enough, my performance sucks, although it's hard to talk about 2 billion multiplies per second and the word sucks in the same sentence. But okay, so 2 billion, 9 billion, 12 billion. Okay, and you can see there's a pretty good jump from 32 to 64. So it must have to swap out. Well, we know it swaps out. 128 is a little bit better, but at 128, it really doesn't get better if you use more. That is, I would essentially call these three equal. But anyway, this is the kind of thing that you'll get. And if we put another loop in there, we could loop through data set size. And like you saw on the other graphs, small data set sizes give you not so great performance because the setup time is not being amortized enough. So there we have it. There we are looking at Cuda code. You've seen what the code looks like. You've talked about how it really works. And this is the process for running it.